So now we'll shift topics. So that was sort of a summary of the issues here in terms of wireless. Now I want to talk about topology. Okay, this is still a physical layer idea, okay? I want to talk about how cables, and we'll put up here media too. In some ways this counts toward wireless, but it's normally just, you know, in terms of if we want to put an actual cable down, how do the cables need to go? All right, so let's go through them. We can do this easy enough. Type 1 is called point-to-point. All right, so if I have a point-to-point topology, I'll just draw my client here. I'm going to have one cable that runs between two hosts, okay? This is the simplest one, but you can make a network of how many hosts would this give you? How many hosts can be on my network in a point-to-point topology? 2. I get 2 and that's it. So this is kind of a small network. That kind of sucks, okay? This does rarely come up. There are times, for example, when you need to take a server off of a bigger network and bring it over and just connect to it directly. And hey, maybe you only have a cable with you and you need to network with your friend. I don't know, but you can do that too. Okay, but this is a point-to-point, and obviously it's going to be a small network. Very small network. The second one, second topology, is called a star topology. A star topology means we're connecting to a central device. And I'll draw a switch here. And what we can do is we can have several stations or several hosts connected into this central device. So several stations connecting to a central device. And again, it's normally a switch there. The great thing about a star is we have what's called multiple simultaneous conversations. What can happen when we have a switch like this is, for example, this station here can communicate with this station, while at the same exact time, this station here can communicate with this station. Right? Now, we can also see that maybe this station could talk to this one, and if we added another station, they could connect in there too. Okay? So this is multiple simultaneous conversations. All right? This is best suited, by the way, for a phone type situation. I've drawn PCs here, but a phone makes the most sense. This might, I don't know, you could think about this like instant messaging. Like these two people can be having an instant message conversation while these two people are, these two people are, and these two people are. Now, for the most part, we know on a network, people on a network, like, you know, connected to the internet or even in a lab, aren't talking, or their computers aren't talking to the other computers in the lab. They're all computers are talking to somewhere else. All right? To do that, you can do this other topology. We call this next one an extended star. And the way an extended star works is you might have a star just like I drew, and I'm not going to draw all this stuff on it. Okay, so I have a star network here. Oops, you need to take my head off, man. I need to fix my hair there. Oops, in the mirror. I need to scoot that up. I'll just scoot that up then, if I lost my operator for a second. Or maybe he wanted me to do that. Passive aggressive. All right, so there's my star. So there's my one star. That might be this star. Let's think about, okay, I've got, one lab in a building, computer lab in a building. Let's say there's a lab on the other side of the building. And so there's another star that might be over here. And we should hopefully understand, and we already did this with that one hands-on where we did the switches, that I can just run a cable across, right? What do we call this cable running between the switches? This is a trunk line, okay? So I run a trunk line between the two, and now I've extended my star. And for the most part, and I did this in the last one too, you will normally have, a few stars here. And the middle one we will call the core, okay? And the thing we worry about with the core is sort of the central part of the network. So it's the center of the network. This one needs to be high performance, because what we need to do is this needs to handle all the conversations that need to try to go this way. Let's talk about simultaneous conversations now. So just like up here, we could have, for example, this person talking to someone over here, and I could have, say, some people over here talking over here. Oops, and that doesn't even show up at all. That's okay. So I've got these conversations running over the trunk line, or the different trunk lines. What's the word for that, by the way, the multiple conversations on the trunk line? We call that multiplexing. There we go. So multiple conversations on the trunk line, or the trunk lines have to handle multiple conversations. The core switch has to be able to handle multiple conversations. And so we'll just put there. The ability to have multiple simultaneous conversations on an extended star depends on the speeds of the trunk line and the speeds of that central core switch. Are we good with that? And we talked about this, right? This is going to be fiber typically. If I'm running 100 megabits per second out here, I'd want to run like a 1 gigabit per second here. That way I could handle 10 conversations. This switch here needs to be able to handle all of those gigabit per second conversations, right? And this link also. So this switch is now the core, or a more important thing. And sometimes they call this a hierarchy. See if I can spell hierarchy. That looks like right. H-I-E-R-A-R-C-H-Y. I think that's right. So a hierarchy meaning there's sort of the cool switch, the boss switch at the core, and then there's these department or work group switches are kind of the subordinate switches. That's pretty fun. Right? One other thing to note, if I don't have enough colors of pencil or pen, sorry. With each of these topologies, there is one path between stations. So if I want to go from one station here, there's only one way to get to the other station. Okay? When we're talking about Ethernet, and that's going to be after we do the exam, Ethernet is a one path. It has to have one path. There can only be one path, I guess. And now I'll show you the one that has multiple paths, which is the next one. So our hierarchy, or our topology number 4 is a mesh. And in a mesh topology, we have multiple links. So let's think about, I want to draw it in a big term here. So let's think we have Norfolk here. We have Richmond up here. And we have someone living in Richmond. I don't know who else is out there. Let's see. We have somewhere down here in Raleigh. And let's go up to Delaware. Somewhere in Delaware. Somewhere on the eastern shore. There's probably someone out there on the eastern shore. Well, they aren't going to talk. DC is somewhere out here too. And what we can do in a mesh topology is we can connect them however we want. Okay? Let's go Richmond to Raleigh. All right. Because what we worry about sometimes is, let's say I need to get from Raleigh to Delaware. I can go here through Norfolk, or I can go around through DC to get to Delaware. If I want to go from, DC to Raleigh, I could come down this way, or I could go over this way. All right? So there are multiple routes between, oops. And I'm going to put stations on here, or hosts. Have I been saying stations? One path. I'll put hosts. Hosts is better, okay? So in order to get between two hosts, there might be two different ways to go. There might be 3, there might be 5. If I'm talking about getting to Los Angeles, there might be 20 different ways to get to Los Angeles. This is, I guess we can say it adds redundancy, and we'll just put reliability. Okay, the idea there with the mesh is to add redundancy and reliability. There's multiple routes though, so Ethernet does not support this. Okay, Ethernet as it's written and as the protocol works, you can't go multiple paths between stations. So that was awesome. Mesh, all right? Now we'll get more wacky stuff. This one's even cooler. Is there anything else you need there? No. Topology number 5 is a ring. Now those of you that have been through IT 201 here, you talked about token ring probably. Token ring is not even worth talking about. I mean, who cares? You guys remember, did you learn about it as you pass around the little conch shell? Yeah, see, you guys pass around the conch shell. Oh, yeah. It was pretty pointless. But here I am again, right? So let's talk about, let's just draw these in. Let's do Norfolk. So I got Norfolk. I've got Richmond. I've got DC. And I'm just going to put Delaware. That would make sense, like Wilmington or something, right? All right. So we all know that going between Richmond and Norfolk, we're going to come down 64. We're going to go across the Hampton Roads Bridge Tunnel and get to Norfolk. To get up to Delaware, I got to go up across the Chesapeake Bay Bridge Tunnel, up the eastern shore through Maryland to Delaware. Delaware, I don't know. They're going through Maryland, I don't know, somewhere. They get to DC magically. And then DC, it's pretty easy to get across the Potomac, down to Richmond, a few other rivers along the way. All right, so a ring network. Normally in a ring network, messages get passed around in a circle. And we're used to this with the token ring explanation. So if Richmond is sending a message to, let's even say DC, if Richmond needs to send a message to DC, it's going to send around this way, and the response is going to come from over here. All right, so DC responding back just goes one hop over. So this is groovy. We don't have to worry about passing the token and all that business. We just understand the messages go around in a circle. And if we think about fiber optic cables, since the messages only go one direction, we actually only need one fiber. Can you all see that? Because I need to just go Richmond to Norfolk, Norfolk to Delaware, Delaware to DC, DC to Richmond. So I only need one fiber. I only need to send in the circle. You guys can see if I want to go from Delaware to Richmond, it's just going to go boom, boom. Richmond responds back, boom, boom. Okay, so there's one fiber. Change back to my black, sorry. So one fiber is used. Okay, I didn't pass around that in the class because it's impossible to see. But the fiber that they actually lay down, the cable that they lay down that has the fiber in it is actually a big bundle of cables, okay? Multiple fibers laid. And we've talked about this before too, and that is the reason they lay multiple fibers. You guys remember why? Why do they put like 25 fibers? Why would you do that when you're going from Richmond to Norfolk? Thoughts?
More bandwidth, you can go in both directions.
Okay, more bandwidth. I could go in both directions. That's the thought. The main thing is you want more bandwidth. You want way more bandwidth than you think you'll need, because most of the expense is putting it in the ground. You remember that from last time when we talked about the people that had put their fiber in and then all of a sudden the speed went up by 10 times? And they were really excited. So that's the whole idea here. It's so expensive to send the trucks out and dig the trenches and attach them to the utility poles and all that other stuff that they lay a ton of fibers down. Now, they usually, there's obviously multiple fibers, usually there's 30 or 40 or even 50 fibers in one bundle. And we talked about the telecom crash. You guys remember that, right? So we already know most of them are dark anyway. Normally there is one dark fiber, or for this particular technology, there is one dark fiber. Okay? So there's one fiber used, one fiber is dark. All right? Now if you think about going up here, the reason we put these routers in, right, is we're worried about, you know, for example, there's a big storm in the Chesapeake Bay and a truck or a barge runs into the bridge, boom, takes that out. Well, I still need to get from DC to Raleigh, and I can go this way. If I need to get from Delaware to Raleigh, I can go this way too, okay? So this adds redundancy here. You ready for your redundancy here? So if we talk about, and this is going to be really hard to draw, sorry, I'll use my green pen. If we talk about a barge hitting the cable and cutting it off, so a barge runs into the bridge again, cuts our cable, now our cable's missing, and so if we want to get from Richmond to Delaware, it's just not going to make it. What happens is the Norfolk little device here detects that this is broken. So normally there's sort of these messages always going around, and this thing is like, hey, wait, I'm not hearing, you know, Delaware didn't come back with their response. And so like something's wrong. This is broken. What the Norfolk one does is what's called wrapping the cable. And what they do is where there should be the cables, they just cross them over. This happens inside the device. Are we okay with that? So it actually happens like right there. So we wrap the ring, they call it. If there's a break, they just wrap the ring. And now if we look at, remember Richmond to Delaware was our orange. I'm going to go around the ring, and then I'm going to go back up this fiber that used to be dark, and I'll still get to Delaware. You guys see it? Or no, I need to go to DC, sorry. And I'll still be able to get to DC. Do you see how it just wrapped around?
Yeah, so the dark ones are just back up.
The dark one is there if there's a break. Yeah, it's just a backup line. Okay, so the dark one just stays dark. So we'll put that until a break. Until a break. Then the ring wraps. Okay, there's going to also be a wrap in the Delaware one too. So Delaware is going to be wrapped also, and that means if DC needs to send back to Norfolk, it goes down here. Well, actually that wouldn't work anyway. Whatever. They can go all the directions they need to, because the ring stays in. It gets wrapped and it remains a ring. And then they send out their trucks, right? The guys with the repair trucks. They fix the brake. You have to fix the brake, because another brake isn't going to work anymore. You got to fix that brake, and then it goes in. This is the main thing. This is called a Sonnet Ring. I don't remember what Sonnet stands for. It doesn't really matter. This is highly reliable, and it is a quick recovery. This is almost an instant recovery from a break, and this is how the phone company, if something bad happens, and these fiber optic cables get broken all the time. You know, barges hitting bridges, backhoes digging up stuff. People shoot at them sometimes. The phone company has this, you know, 2-fiber system in these rings because it gives them a quick recovery. Super fast. Yeah, we're all over that. Well, this is awesome. All right, so that's a ring. That's the purpose of a ring. Like I said, no one uses token ring anymore because we all use Ethernet, but they still use these Sonnet rings. In fact, I was talking to a guy a little while back, and he said, if you can imagine in your brain here, they had provided a link for NASA, and it went from Houston to Cape Canaveral, then up to Langley, and then back to Cape Canaveral. And he said, I don't know why, but they leased 2 lines. So they had 2 lines. And it took me a couple years of teaching this class to realize, oh, that was, you know, the NASA wanted a Sonnet ring in case something happened, you know, to this company, that they could at least keep their communication going. That's exciting. Oh, Sonnet ring, cool stuff. All right, we still have more. What number are we on? We're on number 6 now. The 6th one is the last one, best for last, right? The 6th is a bus topology, okay? A bus topology is all hosts are connected to the same media, okay? This is a little like this one, right? We have one cable between hosts. For a bus topology, we have a whole bunch of hosts connected to the same wire, basically. So I'm going to draw this like a little squiggle, okay? I only ever did this with one. When I was at the racetrack, when we started out, they had some of this kind of stuff in, all right? What would happen with this is everyone is basically they're connected to one wire, all right? So if I'm going to be right here. If I want to transmit something that's going to go over here, I'm going to put it into the wire. The whole wire lights up with my signal. You guys following that? Everyone hears my signal, but it just so happens to be destination of that hub, or that host. Are we cool here? So a bus topology, everyone is connected to that same cable. So when we're on a bus, everyone hears all signals. Say, so every 1 and 0 that goes into this line, every person hears. We'll note that. So every bit, that's signals, right? Remember our positive, negative voltage, all that stuff. Every bit that goes into this cable is going to be heard by every station. In addition, at the stations have to decide which stuff is for them. So I'm sending it here. It has to be addressed so that this station knows they're getting it. We're good with that. One worry is if 2 stations transmit at once, then there's interference, okay? I'll put inter, okay? So if I put in, so I was doing this green signal, at the same time, maybe this person decides they want to transmit something too, and they put in an orange signal, those signals are going to interfere with each other and nothing gets through. Are we good with that? So that's like if we were all connected to one cable. Everyone is connected to the same exact cable. We see this with wireless. If we have our access point and we have our stations, I'm supposed to draw these like laptops, sorry. All right? So here's my laptop and I want to send something, so I start sending something. Who else can hear it? Everyone. Remember, this is omnidirectional antenna, right? So it's going, my signal is going everywhere. So wireless is this bus topology, okay? So while I'm transmitting, by the way, so I need to send something to the access point and I need to get a reply back. I will send, and I will not get a reply back from the access point until I stop sending. You guys remember that? So if we go back here, when we talked about a conversation, this was two-way, okay? A conversation means someone can send and receive at the same time. If we're on this kind of system, what was this called? If you can send and receive at the same time, what do we call that? Oh, you guys remember, see? You probably learned this in IT 201. So that's duplex, right? I can send and receive at the same time. So when I'm in this system, in this topology, what can I do? Am I duplex here? What's this one called? They call that simplex. Okay? Half duplex, by the way, is like I can send, I don't remember how it works. I don't remember how it exactly works. But this one is like only half of the thing can happen at a time. So to receive, I have to stop sending. Anyway, so it's simplex. Right? So it's simplex.
Only send in one direction at all. That's still
Oh, that might be half duplex.
I thought half duplex was when you could send in one direction.
I think this one's
It could be
simplex.
on the test or not.
It's not.
Okay.
All right, where are we? It's going. Oh. All right, so that was fun. That's your topologies. You need to know the 6. And let's see. Yeah. That was fun.